USB-C. The Universal Standard, a comprehensive analysis of USB Type-C. The introduction of the USB Type-C connector, commonly referred to as USB-C, marked the most significant shift in peripheral connectivity since the original launch of the Universal Serial Bus in the mid-1990s. For decades, the industry struggled with a fragmented ecosystem of connectors: Type A for computers, Type B for printers, and a confusing array of mini and micro connectors for mobile devices. USB-C was engineered by the USB Implementers Forum to end this fragmentation by providing a single, small, and extremely powerful interface capable of replacing almost every other cable in a technician's kit. It is not merely a new shape for a plug. It is a fundamental rethinking of how power, data, and video signals are negotiated between devices. Physical engineering and the reversible design. The most immediate and celebrated feature of the USB-C connector is its physical symmetry. Unlike every previous version of USB, which required the user to orient the plug correctly before insertion, USB-C is reversible. This was achieved through a highly sophisticated 24-pin design. Inside the connector, the pins are arranged in two mirrored rows of 12. When you flip the cable over, the internal logic of the port automatically detects the orientation and reassigns the signals accordingly. This 24-pin layout is what gives USB-C its incredible versatility. It includes dedicated pins for high-speed data transmission, legacy USB 2.0 support, power delivery, and sideband signals for specialized functions. Because the pins are so densely packed, the connector is surprisingly robust despite its small size. It is designed to handle at least 10,000 insertion and removal cycles, making it durable enough for years of daily use on smartphones and professional laptops alike. Data transmission, from superspeed to USB 4. One of the most common points of confusion for technicians is the distinction between the USB-C connector and the USB data protocol. It is vital to remember that USB-C is just the physical shape, while the data protocol determines how fast information moves. A USB-C cable could be carrying slow USB 2.0 signals, or it could be carrying the cutting-edge USB 4 protocol. USB-C was designed to scale with the industry's needs. Under the USB 3.2 specification, USB-C can utilize two sets of high-speed data lanes simultaneously. This is referred to as multi-lane operation. By using both lanes, the interface can reach speeds of 20 gigabits per second. With the arrival of USB 4, the architecture moved toward a packet-based system similar to Thunderbolt. USB 4 can reach speeds of 40 gigabits per second and even 80 gigabits per second in its latest iterations. This massive bandwidth allows a single USB-C cable to handle the data requirements of high-performance NVMe external drives and high-resolution video streams at the same time without breaking a sweat. Power delivery, the end of the proprietary laptop charger. Before USB-C, almost every laptop manufacturer used a unique, proprietary barrel connector for power. If you lost your charger, you had to buy a specific replacement from the manufacturer. USB-C solved this through a technology called USB Power Delivery, or USB-PD. Unlike standard USB charging, which was limited to small amounts of power for phones, USB-PD allows for a sophisticated negotiation between the charger and the device. When you plug a laptop into a USB-C charger, the two devices talk to each other over a dedicated configuration channel pin. The laptop tells the charger exactly how much voltage and amperage it can safely handle. In the early days, USB-PD was limited to 100 watts, which was enough for most office laptops, but not for powerful gaming machines. However, the latest extended power range specification has increased this limit to an incredible 240 watts. This means that a single standardized USB-C cable can now power almost any portable computer on the market, as well as monitors, docking stations, and high-end professional cameras. Alternate modes, the versatile chameleon. The true superpower of USB-C is its ability to stop being a USB cable and become something else entirely. This is known as alternate mode, or alt mode. Through alt mode, the 24 pins of the USB-C connector can be reconfigured to carry different types of signals. The most common alt mode is DisplayPort alt mode. This allows a computer to send a native DisplayPort video signal directly through the USB-C port. This is why many modern monitors can connect to a laptop with a single USB-C cable that provides video to the screen, connects the monitor's built-in USB hub to the computer, and charges the laptop all at the same time. Other alt modes include HDMI alt mode and, most notably, Thunderbolt alt mode. When a Thunderbolt certified device is plugged in, the USB-C port switches its internal wiring to allow the PCI Express bus of the computer to talk directly to the external device. This convergence is what allows for ultra-fast docking stations and external graphics card enclosures. The technician's challenge: cable identification. While USB-C offers immense power, it has created a significant troubleshooting challenge for technicians. Because all USB-C cables look identical on the outside, it is impossible to know their capabilities just by looking at them. A cable that came with a smartphone might be designed only for charging and slow USB 2.0 data. If a user tries to use that same cable to connect a high-speed hard drive or a 4K monitor, it will fail, and the user will often blame the computer or the device. To solve this, the industry has introduced a series of logos that should be printed on the cable over mold. These logos indicate the maximum data speed, such as 20 or 40 gigabits, and the maximum power capacity, such as 60 or 240 watts. For a technician, the first step in troubleshooting any USB-C issue is to verify that the cable is actually rated for the task. Using a charge-only cable for a high-performance docking station is one of the most common causes of support tickets in a modern office environment. Security and the eMarker chip. Because USB-C cables can carry so much power and data, they are no longer dumb wires. High-performance USB-C cables contain a small integrated circuit inside the connector called an eMarker chip. This chip acts as the cable's ID card. When you plug the cable in, the computer reads the eMarker chip to find out if the cable is safe to handle 100 watts of power or if it is capable of 40 gigabit speeds. If the eMarker chip is missing or reports that the cable is only rated for 60 watts, the computer will automatically limit the charging speed to prevent the cable from overheating or catching fire. This added layer of intelligence is essential for safety, but it also means that cheap, uncertified cables can often lead to reduced performance because they lack the proper chip to tell the computer what they are capable of. Conclusion: the future of the port. USB-C has successfully achieved the goal of becoming the one port to rule them all. It has brought order to the chaos of peripheral connectivity, simplified the lives of mobile users, and provided professional users with unprecedented levels of performance. For the IT technician, mastering the nuances of USB-C, understanding the difference between the physical connector and the underlying protocols, knowing the limits of power delivery, and being able to identify the correct cables for the job is a foundational requirement for supporting modern hardware. As we move into an era of 80 gigabit speeds and 240 watt charging, USB-C will continue to be the primary gateway through which we interact with our digital world.